So today we're going to finish up taking a look at chapter 3 with some practice problems. And so we've covered all of our learning goals, but we really want to see how these play out when we think about amino acids, peptides, and proteins. So the first problem is, if a protein is in a solution at pH 8 and the pH is changed to 3, which of the following functional groups is altered? And you have a choice. The N-terminus pKa 9.2 gains a proton versus the N-terminus losing a proton. Histidine pKa gaining versus losing. Glutamic acid gaining versus losing. And then the C-terminus pKa gaining versus losing. And so if you're thinking about this problem, what are some of the things you want to take into consideration? Well, you want to pay attention to what your starting pH is, something that is slightly above neutral towards basic, and then what the change is to a very low pH, so something that's more acidic, and then what functional group is that going to impact. So take a moment, think about that. Hopefully, you recognize that glutamic acid with a pKa of 4.25 is one that's going to be impacted by this type of change. Well, let's take another look. So what happens to a buffer to make pH go from 8 to 3? So if I'm going from a pH of 8 to a pH of 3, what's actually happening? Is my hydrogen ion increasing by 5 times? Is it decreasing by 5 times? Is my hydrogen ion increasing by 100,000 times? Or is that hydrogen ion decreasing by 100,000 times? If we take into account that pH is a logarithmic scale, so a very small number in pH represents a very large number in hydrogen ion concentration, then it should be pretty obvious that our hydrogen ion is increasing because our pH of 3 means that we have a very acidic solution. Well, let's take a look at a different type of problem. What's the predominant form of glutamic acid at pH 3.2? So if we take a look at our titration curve, at the top you can see our net charge, so +1, 0, -1, -2. You can also see the change in pH. And at the bottom we can see our equivalence of OH. The predominant form of glutamic acid at pH 3.2, that structure is shown here. Notice I have 3 pKa's that I'm contending with. There's the pKa of the carboxy terminus. That's a pKa of 3.2. There's the pKa of my amino terminus. That's a pKa of 9.67. And then there's the pKa of the R group, which is 4.25. So I have these 3 pKa's that I'm contending with, which means that I'm going to see 3 different structural changes. So when I start out very acidic, everything's protonated, both carboxyls as well as the amino. And the first change, right, when my pH goes from more acidic to less acidic, is that I'm going to deprotonate my carboxy terminus. The next change that I'm going to see, right, these 2 structures are the same, is I'm going to deprotonate my other carboxylic acid. The last change that I'm going to see, again, these 2 structures are the same, is the deprotonation of my amino terminus. So notice, right, when I'm at low pH, so below 2.0, I have a net positive charge because everything's protonated. After the addition of 1 equivalent of base, however, now I have no net charge. And if I'm looking at the halfway point, right, of pKa being equal to pH of 3.2, and the first equivalence point, I can figure out, right, so 3.2 plus 4.25, I divide that by 2, that's 3.7. This is the isoelectric point of glutamic acid because, again, that's where the net charge is 0. If I were to add more hydroxide, it's going to remove my second acidic proton. So at physiological pH, this amino acid actually carries a formal negative charge with an isoelectric point pH of 3.7. From a different perspective now, if I were to use paper chromatography with a nonpolar solvent, such as the mobile phase, with a nonpolar solvent in the mobile phase, which amino acid would migrate farthest up the paper? So would that be lysine, glutamic acid, serine, or leucine? So if we're thinking about this, right, what we really need to do is know what the structure looks like, right? What is the structure of lysine? Well, that's a positively charged amino acid. What about the structure of glutamic acid? Well, that's going to have a carboxylic acid, right? So it actually has 3 pKa's, just like lysine, although this has a tendency, once it's deprotonated, to become negative. Serine has a hydroxyl group, and then there's leucine. Well, leucine is just carbons and hydrogens. So if I had to choose something that was going to move in a nonpolar solvent, I would likely choose leucine. And if I were to look at, say, for example, the RF values of these respectively, I see that leucine is very high compared to serine, compared to lysine, and compared to glutamic acid. So leucine wins out by a fair margin. So what does lysine look like then at a pH of 5? So I need to take a minute and think about what I know in terms of that structure. So I know that my carboxyl group and my amino group and my hydrogen are all going to be the same. It's really the R group that's going to be different. So if I think about what I know in terms of that structure, I know that I have 4 CH2s and then this NH3 plus that's on the very end. And so it makes sense that my structure at low pH would have everything protonated, and that my first pKa is going to deprotonate my carboxylic acid. That's a trend that we should always know to be true. If I take that molecule then and I deprotonate again, now I have this question of, well, which one of these two goes first? Well, likely it's going to be the amino terminus. So that gets deprotonated. And then, right, my last deprotonation is the other amino on the R group of the lysine. So if you take a look at your pKa's, 2.1, 8.95, and 10.53, I can actually see when I'm going to see those protons removed. So at a low pH, basic amino acids are going to have a net positive charge, and that's going to decrease as those groups are deprotonated. And the isoelectric point in this case will occur at approximately a pH of 9.74, which I can determine based on my 2 pKa's. What is the isoelectric point of the peptide HARE? Well, I'd have to go to a table and look up the pKa values, unless they were kindly given to me, as you have here. And the next thing that you're going to think about is, when is the net charge on that peptide going to be 0? So you're going to have to draw out each of the amino acids that form this peptide. Figure out which of the functional groups are buried because they're part of the covalent bonds that make up the peptide bonds of this molecule, and which of these are exposed. And if there are R groups, do they have a pKa? And once you go through that, you'll be able to figure out when is the net charge 0, and then you'll choose the pKa's that are around that, and that's going to allow you to determine the isoelectric point is 7.58. Last one that we're looking at here is, again, pKa, but this is of a small molecule, not necessarily an amino acid or a peptide. Here we're looking at carbonic acid. So I know that my pKa is 6.32, and I'm told that seltzer water is 0.1 molar carbonic acid and some combination of carbonate at a pH of 6.65. And I want to know, what is the concentration of HCO3 minus in seltzer? So I'm given a couple of pieces of information here that I have to reckon with. I'm given pKa, I'm given pH, and I'm given a concentration. Those 3 things should point me in the direction of an equation, in this case, the Henderson-Hasselbalch equation. So once you plug in what you know, you should be able to solve mathematically for the unknown, in this case, the conjugate base HCO3 minus, or A minus, where HA is my H2CO3. The second part of this problem is, if you were to drink 99 milliliters of seltzer and 1 milliliter of your 5 molar HCl gets released, what's the pH of your stomach contents? And so in this case, you're going to have to figure out what's your concentration of H+, and then use that to be able to determine, right, the pH, and do that using the negative log of the H+ concentration. So when you do that, hopefully you come up with these 2. The last problem that we're going to look at today is a hydropathy plot. So these show the hydrophobic nature of a polypeptide region. They're used to locate the alpha helical transmembrane segments in a peptide. So I want you to identify which could belong to a transmembrane segment. Based on your reading, you should know that the hydrophobic regions are what is above, which means that the only one that qualifies in this case is 3. So those are some examples of some practice problems that are great examples of the ways that you can use the information that we've learned in this chapter. Thanks.